Okay, good afternoon. We've got quite an interesting set of topics this afternoon. First of all, I'm going to go over a question sent to me by one of the class. I won't identify him, but it's an excellent question, and I confess that the problem is in finding simple answers to this. There are none. Basically, these are some questions that we'd like to answer today. How are losses allocated? Now you understand that when the electric utility company was vertically integrated, it owned the generation, transmission, and distribution. It simply paid for the losses, and that was buried into its rates that it negotiated with the Public Utility Commission. So now that we've separated things out, where there's different generators and possibly separate transmission companies, and who pays for the losses. So how are they allocated? Who pays for losses? Now, I'm going to try to give you some answers today, but I may not be able to, and I'm going to do a little bit more digging, and next time we'll cover this as well. Now that's enough. How are transmission costs? Now, what I mean by this is basically the usage. Think of the transmission line as a toll highway. We don't have any around here in Minnesota. They do on the East Coast, where I used to live. They do in Chicago area. You drive along, and in order to get on the main highway, you had to pick up a card. Where I grew up in New York State, it was called the Thomas E. Dewey Thruway. It was just one of the very first super highways, and to get on, you picked up a card, and the card said that from the location where you started, then it told you how much it would cost. It's a fixed amount to get off at the point you got off, and the further you went, the more they charged you. So when you finally got off, you handed them the card, and they said, okay, that's $3.50. If you only went a couple miles, it might only be 30 cents. So and so forth. Well, that's a usage charge based on the distance. Okay. So how are transmission costs charged? And both for bilateral and for if you're operating in the market. So we'll come back to that later in the lecture. I'm going to go through the rest of these notes. I'm going to put some nice notes in the problem session, along with the notes that we're using today in class. I hope I can keep these here okay. So, ancillary services. Basically, the first thing that electric generating company does is it converts energy stored in fuel, or it converts energy from falling water, or it converts energy from nuclear fission, and usually the fuel conversion and the nuclear convert it to steam, and that drives a turbine. In the case of hydroelectric, falling water hits a special turbine, and they end up, all of them, rotating a generator which supplies megawatts. So the first service is energy. Okay. But it turns out that there's a lot more to operating a power system than energy. And what we see here, I love this little picture. What we see here is this will be the shaft of a hydro system valve, and we want to regulate the generator, and so we have this device here, which has got a motor and a piston in it, and you can see it here. And so here's this device. It's gonna swing this thing back and forth like this, and that regulates the hydro valve, and that hydro valve then controls how much water. So this thing is adjusting the valve, necessary for frequency control. Remember, if you have an increase in load and this generator is participating in frequency, then this guy has to open the valve a little more, whichever way open is. I don't know on this figure. So there's an actual physical picture of something that's helping to supply an ancillary service. Here's a list of ancillary services, and I think it goes on for about 2 pages here. Now, regulation, of course, is frequency control. We've dealt with that. So what we're saying is, well, you know, if you're going to be an independent generator and you are going to connect up to the power system, we're going to require that you become part of the frequency control system. You have to have governors on your generators. You have to have control systems so that we can change your set point up and down in response to load controls or in response to loss of generation when the frequency goes down real fast. That's regulation. You're going to be part of the frequency control, and you say, but wait a minute. I'm an independent generator. My stockholders, we got together and we decided to build a power plant. We've contracted with a gas company to supply us with gas as fuel, and we're building a power plant, and we just want to sell energy. We don't want to be part of the frequency control system. So we'd rather not. And the problem is that and let me say it this way: there is a cost. There is a cost to be running the valve open and close, up and down, up and down, up and down. The mechanical parts of it wear out. It does not promote efficient. Very, very efficient generator would like to go to a certain output and just sit there fixed, but and not participate in frequency regulation. So there's a cost to the generating company to do this frequency control. Well, you can't have everybody say that they don't want to do it, because then there's no frequency control. And the way that we balance load and generation is everybody participates in frequency control. So basically they have to do certain things. They have to be good citizens, if you will, and participate, and that's one of them. Load following is basically saying that if the load is ramping up and down, then I have to have generators that are going to ramp up and down at a certain speed. Now, some of these ancillary services are optional for you to participate in, as long as they have sufficient generators that will participate in the ancillary service of one particular type, like load following. Then that's fine. Energy imbalance says that I may have to overgenerate or undergenerate from my contracts to make sure that the net megawatt hours generated is equal to the net megawatt hours of load plus losses. And somebody has to be following that accurately and called upon to go up and down. Obviously, all of those in a regulated utility where the vertically integrated, they just did it because it was something that was necessary to be done. There was we didn't have to. So let's come over here and we'll put it in a slightly different color on here. How do you get people to participate in this? That maybe they for some they have to, but maybe others they don't have to. You basically price the ancillary service, and then buy from the generators. Now, that means they have to be willing, and they have to, maybe the generator may set the ancillary service price, and then we buy from them, and there can be an auction. There can be an ancillary service auction. All right, so energy imbalance. This is to match megawatt hours that load and generation. Operating reserve. Now you might have a large generator that says, I want to make as much money as I can, and I'm going to sell at a good price. Therefore, I want to operate my generator at the peak, at the maximum output, right up at the max. Now, the problem if everybody does that is that if we lose one generator on the system, then everybody's up at their max. There's no room for people to increase their output, and the system you're gonna have to shed load in order to bring about a match, and you don't want to do that. So somebody has to operate below their max, and that difference is the spinning reserve. If the unit is on and it's synchronized, it's spinning, and the difference between that amount and the maximum for that generator, called spinning reserve. Again, it's a service, and you could have a big generator that says, "I'm not going to do that." Well, maybe it has to buy its way. Maybe it has to say, "Look, I'll pay you so that I don't have to participate." That's legitimate. There's another thing called Supplemental Reserve, which may mean I keep a unit that's on standby. I can start it up relatively quickly, and bring it online in case the system needs it. Backup supply is simply says I have a generator that I don't normally operate except during peak times, but I'll make it available in case there's an emergency as a so-called backup. So those are all things, but again, in order to make you have to either dictate by operating edict from the government that says if you want to be on the system, you have to provide so much spinning reserve. And any of these, they're priced, and you buy it from the generator. Here's more. System control. That means somebody has to build a building, install computer systems, train people, etc. The system control is expensive. Somebody has to provide it. Now, essentially, that's a service. They contract with usually the transmission owner for that region, but that's a service that it provides and is paid to provide that system control, because it's a lot of money. Building a building, maintaining the computer systems, training hundreds of people is an expense. Okay. Dynamic scheduling is similar to the reserve, but it's just a matter of providing units that can ramp up and down so that you can follow loads that go up and down. Now, that might be a service. Okay, so these were all the ones on the previous page all had to do with generation going up and down. And now on this page, we're getting away from strictly the mechanical issues of generations spinning away on the system. Reactive power and voltage control from generation simply says that somebody has to supply reactive power. Okay, and when we do a power flow, there's P going into the system and there's reactive power, Q. If you don't supply reactive power from that generator, the voltage is going to start to drop. The truth be told, the way that you get it to push reactive power into the network is by raising the voltage, which involves increasing the current flow on the rotor of a standard generator, and that increases the field, and that causes the more reactive power to go out into the network. It also is a way of regulating the voltage. So if I want to regulate the voltage on the power system, the primary way that I regulate the voltage is by the generators. Let me come back here to our page. Now I'll jump back here once in a while. Voltage control, and we also can call that VAR, VAR control or VAR support. So how is voltage good? The primary way we control voltage is with the generator exciter. and but the exciter current will cause the will change the voltage magnitude at the generator, and that will help to keep the voltage regulated throughout the system. They all participate in that. Now, there are other ways to control voltage. It's not just the generator. Tap changing transformers, very simple diagram is to just look like this. Usually they're auto transformers, but I'm just going to assume that we have different taps here, and we have a mechanism that can move this up and down and take different taps. So we can literally change the tap ratio, not a whole lot. But if I need to raise the voltage 1%, I can change it 1 or 2 taps and the voltage will go up or down. And this is usually done, this is the high voltage side, and this is low voltage or distribution side over here. And that controls the voltage. If the voltage is varying on the high voltage, I can hopefully keep it within that desirable plus or minus 5%. So this is our. So that's another. We can use switched capacitors. You have a circuit breaker and you have a capacitor, and that's just a way of adding VARs without having to have a generator. You add VARs by switching in the capacitor. The problem with that one is that you switch in, you get an integral amount of VARs. You can't just add a little bit. Maybe you have 5 or 6 capacitors, so you have individual switches on them, so you can add, but they're still steps. If you want to regulate voltage without a transformer, you have what's called a reactive compensator, reactive power reactive compensator, which basically is power electronics. And it can do Q in, it can take Q out if it's necessary, and it can regulate voltage by regulating Q in and out of the system. And they can do it in huge amounts compared to capacitors, and they can adjust that Q exactly as necessary to keep voltage at a certain value. The reactive compensators are generally installed in a substation that has to do with a high voltage transmission link, and they have the ability to increase the capacity of that link, because as the link loads up, the voltage will drop at one end, and this reactive compensator can bring that voltage back into its design point. So that's an example, but I wanted you to know that the primary way that's done is with the generators. All right, so let's get back to transmission losses. We're gonna go back over that at the end, but I want real power transmission losses. Who supplies it? If you want somebody to supply it, you're gonna have to pay for it. Generally, this is done by requiring all the generators to pay for. And I shouldn't say pay, it's not dollars, it's to pay in megawatt hours, to put a certain amount of energy into the network that just covers the losses. Network stability services. It may be that you have an unstable system for different combinations of generators. And so in the open market, you just can't schedule the way you want because you need generators to be on just basically to give you some inertia in the system and provide inertia. So that's considered an ancillary service. This is an interesting one. Black start. When you've had a blackout, how do you get the power back on? Like everybody's out. How to restart. Now, if you're in the United States, let's say North America, or if you're in Europe, or some other large continent that has a large power grid, generally it doesn't all go out in a blackout. It only blacks out part of it. And in that case, you connect. So how do you restart? So one way of doing that is to connect to a running system. You can set up your transmission system so that you can close breakers and bring power from an operating system into your system. Now, what do you need the power for? Well, if you have a large power plant, you need power to run pumps, to run fans, to run the myriad of equipment that moves the fuel and so on and so forth. And you have to have all that running before you can start to generate power. So you need power to get the plant up and running. If you're a hydro plant, probably you can do it. Now, if you only have that valve mechanism that I showed you before, well, you still need some power to adjust the valves. Now, if you had a chain or a geared mechanism where you could adjust the valve with a manual, let's say turning a crank or something like that, that would be very useful, because then the hydroelectric plant doesn't need an outside source of power in order to start producing power. So you can, that's what's called black start capability. Hydro provides black start. The truth is, so do wind generators, so do solar photovoltaic systems. Don't need to have power coming in order for them to produce power, begin to produce power. But most large power plants need to be connected up and to receive power in order to get things up and running again and start generating. That's why if you have a blackout, it takes many hours, let's say 12, 18, 24 hours of work to restart the whole system. It's not an easy thing to do. All right, let me go through some of these. We've talked about them. Regulation you got to have adequate response capability under AGC. So that means that the generator has to be able to go up and down. Continuously balance the control area supply with the load variations. Load following. Meet the hour-to-hour daily load variation is not covered by the regulation service. So again, if you have a load and every day the load ramps up like this for an hour, then you have to have generators that can follow that. If you don't, and if the load goes up and the generators kind of follow later on, then the frequency is going to be dropping off, because it's going to get that power by slowing everything down. So you got to have some generators that follow it, load following. Here's the basic automatic generation control. We talked about this. We have tie lines, and we have this block here. If you remember, it used to be called load frequency control. It's also called AGC. And we generate an ACE signal, and we go through the desired generation. We decide how that's allocated, and then each unit gets a signal to a unit controller, which goes out, raise, lower, and actual generator. This stands for actual generation. It's a megawatt. So this basically raise lower there's two ways of controlling a generator. One is to send a set point that says, give me that many megawatts, and the control system at the generator will run it up and down to give you that much. Or you can have this whole AGC system say raise, 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 and the generator is supposed to come up a little each time you tell it to raise. And then if the frequency starts turning the other way, you say lower. So it might be raise, raise, lower, raise, raise, lower. I was in the Southern California Edison control room one time during the peak hour in the afternoon, and all the generators were getting raise commands just continuously. And I said to somebody later on, I said, boy. And he said they were raising as much as they could, as fast as they could, trying to follow the load going up. And they just had to keep raising, raising, raising until they met the peak, and until the peak started to turn around and go back down. Energy imbalance, mismatch between the energy scheduled at the point of receipt to the point of delivery and the actual metered flow. So the idea here is that I may have contracted with a neighbor for so many megawatt hours, but we didn't do a good job of controlling it, and the neighbor is saying, you're cheating me, you're shorting me here. So the idea is that the control center must be able to make up the deficit or absorb the excess. That's what that service is all about, that energy imbalance. Here's a diagram. Generator A is a contract to supply load C, fails to deliver all the power called for in the contract. Generator B makes up the difference as an imbalance service. So there is a service, see, and is paid by the transmission operator. Well, he's paid. This guy is not going to get everything he thinks he's supposed to get, because he didn't pay. He didn't send all the power. But they want to keep load C happy, so B comes along and says, "I'll give you that extra megawatt hour to keep him from getting mad." Operating reserve spinning generation capacity synchronized to the system. That's always the case. That is unloaded in excess of the quantity required to serve the current anticipated demand, able to respond immediately. So if this is our generator, and here's the Pmax, and here's Pmin, then if I'm operating right here, if I'm operating here, Well, then the difference here is the reserve. And what it assumes is that if called upon, this generator can raise up to this amount. So that's the spinning reserve that he has. It says able to respond immediately. It's able to start going up immediately. It can't zip over here that fast, but it can start to move immediately. That's very, very important. As opposed to saying, well, suddenly I've lost a generator someplace. Let's start one up. And when we get it started, we'll make up for the loss of that generator. That could be hours. I don't want to wait hours. If I have a loss of a generator, I want to be able to get up. And so I call on a large number of generators to move up. And if I have a bunch of these generators then down here, let's just draw it like this. They're different size generators. Here's a small one. So this is the P-max. Here's the max. P-max, P-max. And I operate the generators like this. Then this much plus this much plus this much plus this much added together is the spinning reserve. It's considered megawatts. And it better be enough to make up for the loss of one unit someplace. Make up for the loss of one unit. And they have very strict rules as to how much reserve you are expected to carry on your generators. How are we doing here? 8. I'm looking at the clock thinking I better kind of talk a little faster. Supplemental reserve backup. So we lose a generator, I can start one. But backup supplemental means that I switch it in. I start it up. Spinning reserve. Here's what happens to the. Now this is on a 50 hertz system. Those of you from countries other than the U.S. and Central America here, you'll see. It's going along nice at 50 hertz. You lose a generator. Boom. The generator, the frequency drops, and then the governors take over and they begin to restore frequency. But if you don't have enough spinning reserve, this is apt to just keep going, and then it gets very dangerous. Once the frequency gets low enough, generators will switch off. They're not allowed to operate them below a certain frequency. And they have automatic equipment that'll just open the valves, open the circuit breaker, and just disconnect the generator. Well, you don't want that to happen to too many generators, or your system blacks out. Supplemental reserve, unsynchronized, interruptible load. Now, it's interesting to say, well, is that a reserve? Yes, it is. If I have a loss of a generator and I can interrupt load sufficient to match what was lost, then I balance the system up. So it's a different way of backing up the system. Backup supply, we talked about replace an outage or to cover a portion of a customer's load that exceeds generation. System control is the system control center is responsible for reliability, minimize transmission, constraint problems, coordinate restoration. Dynamic scheduling is a service that provides for the real-time metering and telemetering, computer software to electronically move a portion. Now we'll talk about what this dynamic scheduling is in a minute, but we'll come to this. I know I have a diagram later on. Here's a system control center. This is an old picture. How do you know it's an old picture? I'll give you a little hint as to how to look at these sometimes. You see this? Do you know what that is? That's a cathode ray tube computer monitor. You have seen them. We don't use them anymore. They're all flat screen. I've given lots of talks about control centers, and I had to make sure that I went through the talks replacing the pictures that had these things with pictures with flat screen. So this is a picture that came from the 1990s. It's in San Diego. That's a system control center where we have monitors, and usually people, sometimes they have levels so that they have a map board here. The map board, you can't see it in this picture, but the map board has lights and some numerical displays, and it represents a map of the electrical transmission system. And I've had some of these operators tell me that the nice thing about the map board is they can walk into the control room, look at the map board, and get an instant overview of what's going on in the system without having to poke away at different displays and things like that. It's all up there. Today, the map boards are usually replaced by just big screens, big flat screens. And this diagram is on the flat screen display. Here is a dynamic scheduling. We have a control area A and B. But this is let's say this is a plant over here that's going to ramp. It's going to ramp its load up, and then it's going to ramp it down even faster, and then it's going to ramp it up again. It's doing some process, and it uses power, and then it doesn't, then it uses power. And this guy says, I will provide a service to regulate the system and follow this guy. And what it is this generator is connected inside control area B. And what it does is it adjusts the schedule up and down. You remember that the AGC needs a schedule of interchange. Well, normally that's fixed for the hour. But in this case, that schedule goes up and down as this load goes up and down. They have to telemeter it back so they can adjust the schedule of both companies. But it's a way of doing that. Incidentally, a very interesting service that was in use on one of the Minnesota utilities, Otter Tail Power. You had this here's the Canadian border. Here's the USA, and we'll just draw Minnesota. Here's Minnesota. This is usually a latitude line, although there's some bumps and things in it. And up here, Manitoba Power, and here it's Otter Tail Power Company. And I'm not sure that they still do this, but Otter Tail Power Company contracted with Manitoba. This system up here is hydro. Now, hydro generators can go up and down much faster, much easier than large steam generating units. And so basically, when they had a load down here that changed, let's say it went up, the schedule from here to here would be adjusted so that the flow going into Otter Tail from Manitoba would go up and down. And so Manitoba provided regulation services for Otter Tail. I always thought that was a very interesting way of providing regulation. We talked about reactive power and voltage control from generation sources. Very important. Real power transmission losses. We named a few here. We said here's a generator that can supply Q. Here's a reactive compensator, which is basically electronics, and it supplies Q. I'm going to put the crossover, and then we have the word LTC stands for load tap changing transformer. And it has taps that'll go up and down. That's this kind of mechanism that we talked about. We have all these taps. And there's literally a mechanical gears and cams and so on that move the tap up and down to keep the voltage constant over here. Reactive supply voltage control. But the primary control is still at the large generators. Transmission losses. Again, the transmission losses, I squared R. The generators have to supply that. This is power here that makes up for the losses. Network stability, procurement, operation, maintenance of special equipment at generator to retain stable operating, and then they call what they call the power system stabilizers, dynamic braking. These are very special devices. Power system stabilizer allows them to control the voltage on the generator very, very rapidly to damp out oscillations on the system. Black start says that you've had a blackout. How do you get the system to come back on? Now here. You can read it. You can read it. And these are all the ones that we've kind of listed here. Regulation, load following, and so forth. We've gone through all of these, and they're numbered. Reliability, what's in the circle for reliability, we've got the numbers in there. Facilitate access and enable markets. Now we put number 8. Dynamic scheduling is an example of that. This circle here. Oh, pardon me. Also 1, 4, 5, 7, 9 also are in this circle. Provide equity in the way the system operates. This was a NERC working paper. And this is a diagram. You can see here that there are reliability objectives, physical capabilities, and control capabilities. And so you have continuous generation, balance, transmission system, security, emergency preparedness. This is a interconnected operations services. This is the kind of thing that we've talked about all these things. We're putting them into different categories of the system control because some of them have to do with reliability, some of them have to do with the physical capability, and some of them the control capability. Now, I'm a generator, or I'm a company, and I really just want to supply megawatts and charge my customers a fair price, and I know that they're going to buy, and I'm going to make money. They're happy with my price. I'm making money. Why are you bothering me with all this ancillary stuff? All I'm going to do is supply to my customers. Leave me alone, okay? Well, the problem is, as we said, that the system needs to operate. The system needs to operate. It's like, it's like saying I'm a trucking company. All I want to do is deliver goods from the factory to the customer warehouse, which is in another state. I just want to drive my trucks. But somebody has to maintain the highways. Somebody has to maintain the highways. Somebody has to maintain the signals, and somebody has to pay for the plowing in the wintertime of the snow, things like that. So you have to, and those services are paid. In the U.S., the payment for using the roads is done through a tax on the fuel. The more you use the more you use the roads, the more fuel you burn, therefore the more you'll pay. And that tax covers those kind of things. We'll talk later again about the cost, how we collect dollars for ancillary services. But there are so-called cost-based versus market-based. Cost-based says when there's a natural monopoly, for example, when it is impossible to buy megavars from an outside supplier, then somebody has a monopoly, and we're not going to let them at that point simply go through and charge whatever they want. No way. When they have a monopoly, then we fix the price. If there's many different suppliers of reactive power, well, go ahead, set your price. If your neighbor's price is lower, we're going to buy from them. Market-based, well, that's the definition of market-based. When there are ample suppliers competing for your business, then they have to, they can ask a price set by their costs plus some profit. Basic quantification. This is kind of general reserves and sort of megawatt capacity, regulation and energy imbalance, or megawatt hours. Reactive supply is megavars and things like this. These are some of the basic units. Determine the amount of each ancillary service needed to support a transaction. Okay, so for a particular transaction, now one of the things that happen is, remember, we always talked about the fact that this guy wants to put power in and he wants to take it out. And that's a transaction. So the transaction has got so many megawatts. And it's got a start time, an end time, a source, and a delivery. There it is. What are the ancillary services to support transactions? Okay. We could say the ancillary services are an amount per megawatt, an amount per megawatt hour of the transaction, impact of the transaction on the transmission system. Now that's interesting, how much of the transmission system gets used. And so we went through here and said, identify the equipment necessary to supply this service. Online generation, much of it is online generation. Computers, online generation. Notice how much of it is. This is your special stabilizers and things. Offline generation is your system backup. We calculate the annualized capital cost for the equipment identified. Let's get this down. Identify the fixed operation maintenance labor for the equipment. Calculate the incremental operating costs of the equipment identified. Incremental meaning how much is it going to cost to supply this transaction's needs. Calculate the annualized cost of other equipment needed to supply regulation or something like that. And sum them all up. Divide the amount from step 7, dollars per year, by the amount each ancillary service required to support. and you get these amounts: dollars per megawatt of capacity, dollars per hour. These are the units that you'll come up with. And then there's the equipment. We talked. I think I already had that slide. And the service costs again. So here were some examples anyway that I pulled off by running around the internet from ComEd, which is in Chicago. There was this Maine Electric had some, and so did ConEd in New York City. But they vary all over the place. Spinning reserve from ComEd is $23 per megawatt hour. ComEd, that's 58 cents. I see it doesn't make much sense, but these things vary all over the place. Metering is another interesting ancillary service. Somebody has to meter what the loads are consuming. Usually, it's if I'm a private company and I own a distribution system, so then I buy bulk power off the transmission system. But who does the metering? Who owns that meter? Now, this is an old-fashioned watt-hour meter. This is a disc right here that rotates around very, very slowly. It goes around, and as it goes around, these counters up here move, tell you how many megawatt hours. Today, that's all done electronically, and we have what are called automatic meter reading systems, where the meter has a transmitter that sends information to a computer system. Let's say it's connected at a substation, and we communicate with it. But there's another ancillary services, the metering. How do you and really we're used to seeing meters for megawatt hours. Again, this is a standard household megawatt hour meter, and they read it, let's say, once a month, or they read it every few minutes, or they send it over to the substation. How much has the number changed? But we're buying a service. So if you're buying megawatt hours, we invented a meter to measure it. What if I'm buying regulation and load following service? Is the supplier that I'm paying it for doing their job? Is the energy imbalance guy doing his job? How do I meter it? Now, so there, the metering, you could say, is I'm measuring their performance, or I'm measuring that they're really supplying what I'm paying them for. That's a difficult thing. Operating reserve. How do I know that this guy says, I am providing you with 200 megawatts of operating reserve from my 800 megawatt unit? Really? Are you? Well, I'm going to have to see your plant, all your plant data streams, so that I know that the unit was online, and what the megawatt output was, and I'll I'll check some of the pumps and the fans usage to make sure that the plant was capable of supplying. So all of these things are difficult, but that's how do you meter it? You're buying a service from somebody. How do you know they delivered it? How do you know they metered it? A very difficult question that confronts you. Okay, I want to go back for a few minutes now to the questions that I posed at the front. I wrote to one of my former students who works for the New England ISO. So one ISO's answer to our questions. So, who pays for transmission losses? And the answer is in that ISO is the load. Load pays. Now, remember that load pays megawatts times LMP at its bus, and generator is paid the same formula, megawatts times LMP. Yeah, they're going to be different unless there's absolutely no losses on the network, no constraints in effect, and so forth. Load pays the LMP at the location they consume. The generator is paid, and so forth. The money that is left over. Okay, since LMP is not the same at each bus, then megawatts load times LMP at the load bus, and we seem to have a dying pen here. This is not equal to LMP at the generator times the LMP at the generator bus. Now this is what he pays this, and he is paid. And if they're not equal, there's some money left over. There's some money left over. Money left over goes into the congestion revenue fund and the marginal loss revenue fund. This is New England. So let's see. There's a congestion revenue fund and a marginal loss fund. Now, you remember that we said that LMP is equal to the LMP at the reference bus plus, okay, DP loss, DPI at the particular bus times the LMP at the reference, plus there's a congestion component, which we get. There's three components. If there's no losses and there's no congestion, then everybody's got the same, and there's no, all the revenue collected then will be the same, and we would collect the exact same amount that we pay out. I'm sorry. So let's do this. Look at this again. Here's the load bus. Here's the generator bus. We say that the dollars collected is not the same, and so the dollars go into a fund at the ISO, and the congestion revenue fund and a marginal loss. And I wrote, he quoted it in that order, but the marginal loss is this one. And if you will allow me, there's your congestion one over here. The LMP components are calculated, an energy component, that's this guy, a marginal loss component, and a congestion component. The LMP components are only used for settlement purposes. Settlement is when we come back and say, okay, who gets what? Who gets money paid to them? Who has to pay? That's called settlement. That's called settlement. So it's like at the end of the day, there's a settlement process. There's a settlement. Essentially, at the end of the month, they're going to have to get the books straightened out. they will change on the location of the reference bus. This is something that I want the location of the reference bus will change the LMPs. Yes, it will. That's partly, if you remember, we had this DP loss, DPI, and here's the reference bus, and here's bus I, and so if I increase power here, then I have to increase power here, but then there's some losses incurred. But if the reference were right here, right next door, then the losses are much less. So this depends on the location of the reference bus. He said we need some way to separate marginal loss revenue from congestion. We use a load weighted average of all buses as the reference bus. So they have a way of saying, well, we're gonna decide what the bus is. I'm not sure what he means by load weighted average, but they have a way of averaging that over the whole system. Congestion revenue gets paid out. Now we're going to talk about this the next time. Congestion revenue goes to their FTR fund, Financial Transmission Rights. Topic of next lecture. I'm not going to go any further. So this is dollars. The marginal loss revenue goes to the participants based on hourly marginal loss revenue load obligation. Losses are nonlinear, so after paying generators for their extra generation that went to losses, there is some money left over that basically gets paid back to the load. So they have a way of paying this to the participants, mainly the generators. Get this marginal loss because they had to supply it, okay? And if they determine that the amount of revenue that it misses the target, then they may fold some of the money back to the loads. But they make the generators, they pay them for the extra that they generated. The other question, and we have time here. The other question is transmission costs paid. I'll put this. How are transmission costs? And he just starts and says they're not. The FTR auction. Now we're going to again talk about that. Revenue pays for transmission upgrades. So this pays for upgrades. And that means new lines, transformers, etc. As long as it increases the capability of the system. And the congestion revenue we talked about goes to the FTR, what they call the holders. This is all mystery, but we'll go through that next week. In order to load, now I asked him another question. I said, if we use DC OPF. Now, why do we use DC OPF? It's fast. It solves. There's no problem in converging. I can do security constrained OPF by adding security constraints Well, then, where do, so then, how to add losses? And what he says that loss factors are introduced at each node into the model formulation. The loss factor is the change in total system loss. So what they do is they say, here's a reference bus, here's a generator, and here's a load, and it says, I'm gonna go up 1 megawatt at the bus, and withdraw 1 megawatt from here, 1 megawatt. Well, there's a loss component in here. Between the two, the losses factors are nonlinear, calculated based on the AC system model. That's right. They're recalculated, and so they develop a loss component. Well, really what that is, I've seen people do this before. Here's the load, and here I have this little bitsy load over here that goes up and down, and it's not really, and this is to account for losses, so that this is spread all over the whole system, and I put it at a bus, and then as they readjust it every once in a while, and then if the sum of all these on all the load buses equal the total losses of the network, then the total generation will come out, and they've done enough studies to convince themselves that that's an adequate way of doing it without using an ACOPF. Without using an ACOPF. Now that question, let me see if I can find that question. I had it written down here. I don't have it. In any event, oh, here we go. Now, I think we've answered as much as I can at this point. We're going to talk a lot about FTRs next time. Remember that we have the following problem to deal with. And in fact, I even have some software that'll do an FTR auction. We have a system like this, and we have a generator over here, and we have a load, and then we have this guy would like to sell power from here to here, and the red one would like to sell power from here to here, and so forth. And we have a green company where we have a generator here and we have a load up here. So this is A, and this one wants to receive A, and this is B, and this is B, and this is C, and this is C. Well, A says, look, I've got a long way to send my power, and I want to make sure that transaction, I'm going to make a deal with A, and I'm going to sell him the power. I have no idea until the spot market runs whether the transmission system will be overloaded or not. So, in essence, and I love this, I like the terminology, A, B, and C buy an insurance policy that pays them if their transactions cannot get through, and that is called a financial transmission right. But it's an insurance policy. It says, okay, you and the price. What's interesting is the price of the insurance policy, and how much is it worth to have the insurance policy. And so they actually have an auction to determine whether or not, what the prices are. And if A thinks that his deal is so much worth more, well, then he might put a lot more money into his insurance policy. And same for the others as well. So we'll deal with that next Tuesday. That's our topic for next Tuesday is the FTR, so-called insurance policy. Okay, so you will be getting these notes, and we will be ending our lecture right now. So we will see you next Tuesday. Then we will see you next week Thursday at Keller Hall for a last meeting before the final exam. Oh wait, I already did that. Okay, so now I will say goodbye. The meeting will end. Bing, right there.